Let's now look at part 3 of this question. Part 3 comprises two sections, A and B, and let's focus our attention on A. First of all, the question says, deduce the exact value of a particular series, right? We need to think to ourselves, what does the word deduce imply? It means to say we have to use the earlier result. And what is the earlier result in this case? In part 2, we have gotten the following, or we have shown this to be true. N plus 1, n plus 2 is equals to 1/4, right? This was what we had gotten from part 2. Now we have to try to incorporate our result in part 2 into our working in this case. Now how do we do this? We notice first of all that the terms in our current given series is not exactly the same as the terms in part 2. Well, they are not identical, but they look quite similar. It seems that the denominator consists of factors behaving in the same manner. And what do we mean by that? Let's take a look at our current given series. Notice that the denominator of the terms consists 3 consecutive factors. These are n plus 1, n plus 2, and n plus 3. Similarly, if you look at part 2, we have also 3 consecutive factors n plus 1, n plus 2. So all these factors, they actually differ by 1, right? Now since we have to try to weave our result in part 2 into our working in this case, we need to think of how we can relate the differences of terms together. And we do notice that if we were to subtract 1 from n plus 1, it gives us n. If we have n plus 2 minus 1, it gives us n plus 1. If we have n plus 3 minus 1, it gives us n plus 2. So it seems that what we are currently doing is that we are replacing n with n minus 1, right? Let me just take away all this. And we can start our official working by replacing n with n minus 1. So this is n minus 1 equals to 20. All right, and for the terms, it will have n minus 1 plus 1, n minus 1 plus 2, n minus 1 plus 3. All right, so if you were to make things look a little bit neater, this will be n equals to 2, 21, 1 over n, n plus 1, n plus 2. And great, now we do see that terms in this specific series is actually the same as the terms that we see earlier on in this case, right? However, we still have things that differ from part 2. And what is this that's different? It is the lower limit of n equals to 2 versus the lower limit of n equals to 1. All right, and since we are doing a deduction question, we cannot simply recalculate our series and redo our methods of differences. We have to try to get our result, put our expression on this right-hand side into our working. Okay, so perhaps since we are currently calculating by adding up the second term all the way to the 21st term, what if we start from the first term, add all the way up to the 21st term? right? Then this will be better because the lower limit will correspond to our part 2. But can we say that these two series are equal just like that? No, we can't, because in this case, we were adding up from the first term to the 21st term. In this case, we were adding up from the second term to 21st term. So that means to say we have to balance them out. And we can balance it out by subtracting the first term in this case, right? And how do we write the first term? Well, we see that for the first term, n will be equals to 1. So we will have 1 over 1. Then we will have 1 plus 1, which gives us 2, all right? And then we have 1 plus 2. Okay, this is the first term. Makes sense because we are basically just replacing our n, in this case, with 1, right? Because it's the first term. Okay, so then now we can safely use our part 2's result and rewrite the series to become 1/4 minus, okay, the upper limit now is 21, so we can just replace capital N with 21. 21 plus 2 minus 1 over 6. Okay, and then our final result would be 125 over 1518. All right, I know some of us will be a bit confused with this working here, so maybe let's just write things down clearer for our own understanding. Right, so here in this case we are summing up from second term to the 21st term, whereas in the next case we are summing up from the first term to the 21st term. Okay, and therefore for us to equate them to be the same, we have to minus away u1 from this portion, right? So that's why we can subtract it and then realize that they are equivalent, which is actually what we are doing in this case here. Okay, so that's basically the end of part A, and we do realize that it is the exact value. Okay, it is in a proper fraction form, so please do not convert this into decimals. All right, now that we are done with part A, let's look at part B of this question. In this question, we are also asked to deduce the exact value of another series. Okay, and what does the word deduce imply? It means to say that we have to use the previous result. Okay, and we have copied down part 2 into this page so that it's easier to refer to. All right, so let's move into looking at the series that we are currently given. What do we notice is that the numerator looks more complicated, and more importantly, the denominator now consists of 4 consecutive factors. All right, whereas all along we have been working with 3 consecutive factors. So this means to say that in order for us to use the previous result, we have to kind of split the fraction so that there are now 3 consecutive factors in the denominator instead of having 4. Well, we can do some brute force method. Perhaps the first idea that comes to your mind would be to split it into 2n and 3 for the numerator. So I have done this out, and maybe this is also what you have tried. Okay, so let's take a look at this. In the first series over here, it looks quite ideal because we can cancel out n. And then it gives us a series where the terms have denominators with consecutive factors, and there are only 3 factors. This is great. It's something that resembles part A that we were working on previously. But in this second series that we are looking at, it is not that ideal because we have 4 consecutive factors in our terms. Alright, so it is not fantastic. So this means to say that we have to try to split this original fraction into 2 fractions such that the denominator only has 3 consecutive factors. This means to say maybe we can do some thinking. Okay, so if you want to write this as a rough working, by all means. Alright, so in my mind, this is what I would be processing. I want to write it something like this, whereby my numerator, alright, would be able to be cancelled out with the last factor so that I have 3 consecutive factors, and I can also cancel out, alright, with the first factor so that again I only have 3 consecutive factors in my denominator. This means to say that perhaps I can fill in this blank here with n plus 3 so that I can cancel off with n plus 3, and perhaps I can fill this up with n so that I can cancel off with n. And then we are able to work with a series with terms consisting 3 consecutive factors in the denominator. Interestingly, we do realize that n plus 3 plus n actually gives us 2n plus 3. So maybe this is how we can approach the question. So let's go back to the official working and write this down properly. So I can rewrite my series to be in this format, right? This is equals to, I can split it up into n plus 3 and in this case now the numerator would be n, and this is great because I can cancel off the numerator and denominator, cancel off n and n in this case, and this gives us something that looks more familiar. Plus 1 and plus 2 summation 1 over n plus 1 n plus 2 n plus 3, right? And now we see that this series, it is actually similar to part 2, isn't it? Except now the capital N has been changed to 20. So all we need to do is to change capital N to 20. And for the second series, in this case, do we actually have to recalculate it? The answer is no. And why not? Because it is actually similar to our series in part A. Alright, so we can actually just use our result from part A and write it down instead of recalculating everything. And our final step now in this case is just to sum them up. This gives us a single fraction of 160 over 483. And this concludes part B of this question.